Let's start by throwing away the table of the standard model and begin with a clean slate. We'll start with nothing and go step by step while exploring the standard model. First, let's build an atom. To do this, we need quarks. The nucleus of atoms contains neutrons and protons. These are made of either a combination of 2 up and 1 down quarks in the case of the proton, or 2 down and 1 up quark for the case of the neutron. These quarks come in 2 values of electrical charge. The up quark has a charge of plus 2/3 and the down quark has a charge of negative 1/3. So the total charge of the proton is plus 1 if you add up the charges from 2 up and 1 down quark. Similarly, the total charge of the neutron adds up to 0. We have 2 classes of matter particles in the standard model, leptons and quarks. Matter particles have this special property of spin. They can spin clockwise or counterclockwise. And depending on what way the particle spin is in relation to its direction of motion, it is classified as either a right or left-handed particle. Quarks come in both types, left-handed and right-handed. Now, this aspect of handedness is very important because it turns out to be crucial for how the particles interact. This is something that is completely omitted from the typical representation of the standard model. Left-handed up and down quarks can transform into each other via an interaction of one of the fundamental forces of nature, called the weak force. This is called a charged weak force interaction and is mediated by a W plus boson, which has a charge of plus 1, or a W minus boson, which has a charge of minus 1. This line represents the W boson charged interaction. Now, for some unknown reason, nature turns out to not treat left and right-handed particles the same way, because this interaction does not happen with right-handed quarks. It is not known why. This means that right-handed quarks cannot change into other quarks and remain the same particle always. There is no charged weak interaction between right-handed particles at all. The quarks also have another charge called color charge, or more precisely, each type of quark exists in 3 different colors: red, blue, and green. The color charge allows quarks to interact via another fundamental force of nature, the strong force. The strong force is mediated by another boson called the gluon. This strong force interaction allows 3 quarks of different colors to be bound together to make a proton or neutron in the nucleus of atoms. We can represent this force by showing a triangle between the different colors. Note that the triangle is the same for left and right-handed particles because the strong force, unlike the weak force, does not discriminate between left and right-handed particles. It treats both types of particles the same way. The colors of these quarks are constantly changing by emitting and absorbing gluons. But all 3 quarks must be of the 3 different colors, red, green, and blue, to make a neutral or colorless charge. Any 2 of the 3 quarks can't be the same color at the same time. So far, we have the following for quarks. There are up and down quarks. These quarks can be further split into 2 groups depending on if they are right or left-handed. In each group, there are 3 colors of each quark. So as of now, we have 12 different quarks, 6 different up quarks, and 6 different down quarks. Again, looking at the standard table of the standard model, you might be fooled that there's just 1 up and 1 down quark, but there are really 12, as shown here. You should know that quarks by themselves can never be observed. The theory tells us that only colorless particles can be observed. A colorless particle can only be formed in one of 2 ways. You can either combine quarks of 3 different colors, red, green, and blue, to make a neutral color combination, like in neutrons and protons, which can be observed, or you can combine quarks and antiquarks. Yes, there are antiquarks that carry an anti-color. So there are anti-red, anti-green, and anti-blue antiquarks. When a quark binds to an antiquark, the particle that's formed is called a meson, which can be observed. These color rules come from the strong force. The strong force is mediated by a particle called the gluon. Like glue, it binds quarks tightly together. There are actually 8 different gluons with different combinations of colors. Gluons act as a mechanism to transfer colors from one quark to another. This transfer of colors is what binds quarks together. I made a very detailed video on how this happens using Feynman diagrams if you're interested in knowing the mechanics of this. The gluons are not colorless, but theoretically you could combine them such that you can make a composite ball of gluons that is colorless and could be detectable. But so far, no one has ever detected a glue ball. Now, let's look at the second class of matter particles called leptons. Again, we have two types of leptons in terms of charges. We have the electron with a charge of -1 and the neutrino with a neutral charge of 0. Like with left-handed up and down quarks, the charged weak force can transform left-handed electrons and neutrinos into each other too, via the exchange of the W boson. While both left-handed and right-handed electrons exist, when it comes to neutrinos, for some reason, only left-handed neutrinos exist. Right-handed neutrinos have never been detected. Unlike quarks, leptons do not have any color charge, and so they are not affected by the strong force. This lack of color charge is the main distinction between leptons and quarks. So with that, let's do a quick summary of what we've learned about matter particles thus far. There are two classes of matter particles, quarks and leptons. For the quarks, there are 6 up quarks and 6 down quarks. They carry both electrical charge and color charge. For leptons, there are 2 electrons, left-handed and right-handed, and 1 neutrino, left-handed only. Electrons only carry electrical charge and do not have a color charge. Neutrinos do not carry any electrical charge or color charges. So to sum it up, we have 15 particles so far. Recall that physics is about explaining what we see and not about creating something that we decide. We just observe. We don't make the rules. I say this because for some strange and unknown reason, the universe appears to contain what we call 3 generations of particles. What we have discussed so far was only the first generation of matter particles, but there are 2 more generations. Each generation contains the same number of particles. Thus, we get another 15 from the second generation and 15 more from the third generation. In total, we have 45 particles. The only difference between the generations is that the particles of generation 2 are heavier than generation 1, and the particles of generation 3 are even heavier than generation 2. There is no other difference that we can tell. To this day, scientists have no clear understanding of why there are 3 generations, except the theory just works this way, and the 3 generations match our observations. It turns out that left-handed quarks can not only transform between particles within the same generation, but also across generations to a lower mass particle. So for example, the charm quark, which is the heavier second generation version of the up quark, can decay into a first generation down quark. In terms of leptons, there's nothing in the theory that prevents them from transforming between particles of different generations, but so far this has never been observed. This is, however, an area of current research, and there are signs that this kind of transformation could exist. But as of right now, evidence shows that only quarks transform across generations. Let's move now to the non-matter particles, the bosons. We discussed in some detail the strong force mediated by gluons, which binds the quarks together into composite particles, such as neutrons and protons. We talked a little bit about the electrical charge, the fact that quarks have a charge of either 2/3 or -1/3. The electron and its heavier generations all have a charge of -1, and all neutrinos are neutral, with a charge of 0. The force responsible for this charge is the electromagnetic force, and it interacts with all matter particles except the 3 neutrinos. So we can draw a connection between all these particles. Just like gluons mediate the strong force, photons mediate the electromagnetic force. In other words, the exchange of photons is what confers the electromagnetic force between 2 electrically charged objects. We also talked a bit about the weak force. As I said earlier, only left-handed quarks can transform into one another via the weak force, and only left-handed electrons and neutrinos can transform into each other via the weak force. And these interactions that change one particle to another are made possible by the charged W+ and W- bosons. But these are not the only particles that confer the weak force. A third boson involved in weak interactions is the Z boson. However, it does not have any electrical charge. The exchange of a Z boson acts to only transfer momentum, spin, and energy between particles, while leaving any other properties of interacting particles unaffected. Since there's no transfer of electrical charge, this is referred to as a weak neutral current interaction. Note that the word current just means that a Z particle is exchanged. There's no flow of current like in electricity. Also note that unlike the charged weak force, the neutral weak and electromagnetic forces can interact between both left and right-handed particles. This is because the neutral weak force and the electromagnetic force appear to come from a single force that existed near the beginning of the universe called the electroweak force. I have a video on this if you want to know more details. At this point, we've discussed all particles except one critical one, the grand poobah of fundamental particles that was predicted more than 50 years ago, but only confirmed in 2012 at the Large Hadron Collider in CERN, Switzerland. That particle is, of course, the Higgs boson. This is the particle that gives mass to all massive fundamental particles. And since all matter particles are massive, the Higgs boson connects to all of them. But there is one exception, the neutrino. The Higgs does not interact with them, according to the standard model. So how neutrinos acquire mass remains a mystery. The Higgs particle doesn't care about right and left-handedness and treats both equally. The only bosons that do not interact with the Higgs are the gluons of the strong force and the photons of the electromagnetic force. These two particles thus have zero mass. The amount of mass conferred to these fundamental particles depends on how much they interact with the Higgs field. The greater the interaction, the higher the mass. So for example, the top quark interacts more with the Higgs field than the charm quark, thus gains a higher mass. Likewise, the charm quark interacts more with the field than the up quark, so it has a higher mass than the up quark. For simplicity, you can think of this interaction with the Higgs field as slowing the particle down. The more the interaction, the slower the particles become, and the more mass is conferred. Massless particles like photons do not get slowed down and so travel at the maximum speed allowed by nature, the speed of light. So the final count is the following: 45 matter particles, 8 gluons, 3 weak bosons, 1 photon, and 1 Higgs particle. In total, 58 particles with different handedness, charges, colors, and interactions. This is a full picture of the standard model of particle physics. But you should know that this is not the end of the story. While we have 58 particles, we also have an equivalent amount of antiparticles. Antiparticles are generally the same as regular particles, except they have opposite properties, such as charge. So for example, the anti-electron, called a positron, has a positive charge, whereas the electron has a negative charge. Handedness also changes. So for example, antiparticles of left-handed particles are right-handed. This means that while only left-handed neutrinos exist, only right-handed antineutrinos exist. So the charged weak force only works with right-handed antiparticles, just like it does with left-handed regular particles. To account for antimatter, we would have to add 45 antimatter particles, increasing the total count to 103. Second, we know the standard model is incomplete. This model only tells us what the visible universe is made of, but there's more to the universe than just that. So for example, dark matter and dark energy are not accounted for in this theory. And other mysteries like why neutrinos have mass, how gravity enters the quantum picture, and why there's a matter-antimatter asymmetry in the universe is still unanswered. These are what keeps the standard model from being a theory of everything. So although this is the best, most accurate model of the universe we've got, there is more to be added to this story. And if you're an aspiring physicist, there are lots of things waiting for you to discover.